Good evening. I'm extremely sorry to have to do this in English. I can only imagine at the end of a long working day that you now have to listen to some idiot in your second language. I'm terribly sorry about that. My colleague suggested I could try Latin. But then I imagine it would sound like some weirdo trying to do the equivalent of Shakespearean English and talk about data. So let's stick with English for the moment. And if you behave well, then I'll give you a rendition of Catullus at the end. Okay. Sorry, hello, I'm Jim. And I have a little history with some people around here, which I won't talk about. I learned almost no Italian from them, apart from how to ask for more coffee. That's pretty much our history right there. I'm going to talk about data, and in order to make that subject accessible, I'm going to talk about data in a retail context, because I think that's a context we're all very familiar with, some of us more familiar than others, but even you and I, in our daily lives, we're quite familiar with the aspect of shopping and buying things and so on. And so I'm going to talk about data in that context. Firstly, though, I do have to say thank you for the invitation. It's lovely to be back in Venice. Congratulations to you guys for making it to 10 years old. That's phenomenal in IT. When most startups die within 6 to 12 months, that's an excellent achievement. I work for a company that isn't 10 years old, so I'm jealous. What shall we talk about then? This is what we're going to talk about. I'll talk about where we are in the world of data today. So you may have gathered I have a little history in the integration and enterprise architecture side of things. But for the last 4 years, I've been working in the data space. I've been doing some more computer science-y things. So I'll talk about where we are in data, talk about how we're imprisoning data today. And we'll have a little history lesson regarding a particular Swiss mathematician. And then we'll talk about what I work on, which is this stuff, a particular kind of graph model for storing and querying data. That's what the Neo4j database does, the thing that I work on. I'll teach you very quickly how to do some design in that model. It's a very simple model, a very applicable model. And then, because I'm feeling brave, I'm going to show you some live coding. I'm going to show you how to build the kind of recommendations that Amazon and those kind of big web retailers can give you. But I'm going to do that in 5 minutes, maybe 3 minutes, because I only have 9 minutes and 42 seconds left. Let's get started. So this is where we are today. Thank you, by the way, for sending your schema to me. It was very helpful. And yeah, some of you were like, oh shit, where did you get my schema from? It's not your schema, but you have a schema like this. Marco has many schemas like this. And some of you are super, super clever, and you can see through this schema. You can see through this schema, and you can see the intent of the data model, yeah? Because many of you are very, very skilled at relational databases. When I look at this schema, I just see complexity and risk, and who the designed this? Because I'm going to fire them. It's difficult, actually, because I think what we've done is we've taken the relational model, which of course I was never really meant to do this stuff, and we've really worked hard and we've been very clever at making the relational model do clever things. But when we reach this level of complexity, certainly the person that wrote this schema might understand it today, but will they understand it next week? If you were new joining the project, would you understand this schema? And I have to say that the relational database schemas I've seen over time, I've been simultaneously impressed by and scared of because of their complexity. So I think we've reached a point where tables have done us a great favor for the last 30 or 40 years, but they're not the answer to everything in the 21st century. And of course we know there is this movement called NoSQL, which is the world's stupidest name. It defines itself by the absence of something. That's ridiculous. I can only think of one thing more ridiculously named than that, and that is Neo4j, which is the world's most ridiculously named database. But we have this NoSQL thing going on. It's very interesting, actually. We have key value stores, we have columnar stores, and we have document stores. And these things each give us a different kind of data model against which we can store and access data. So the key value stores give us the illusion of a big hash map. And that's nice. It's a nice simple model against which we can program. And these things tend to have really great operational characteristics around reliability and around scale. Similarly, the column stores have a really nice data model which is nested hash map of hash maps. And they have a nice property that where the keys line up in those hash maps, you get an emergent index through your data. So you get a little more insight into your data. And then finally we have the document stores, and they're very, very comfortable for us because the metaphor is filing cabinet. Put documents in, take documents out, and index those documents. So very, very familiar to us. And this is great because these things are, compared to some of the harder parts of relational databases, very simple to use and feel very pleasant. Now, Martin Fowler, my ex-boss, wrote a really lovely book called NoSQL Distilled, and he wrote it with my ex-colleague Pramod Savage. And in that book, Martin and Pramod observed that those three classes of database share a fundamental similarity. And they say, Martin and Pramod say that these are aggregate databases, insofar as that the data that you store isn't connected or joined, you're storing individual atomized pieces of data. And Fowler and Savage say that these databases work brilliantly when your storage and retrieval pattern is symmetric. So when you store a session, retrieve a session, works great. When you store a customer, retrieve a customer, brilliant. When you store a product, retrieve a product, also great. But when you want to understand at what times of day are certain types of customers purchasing products from certain classifications, then those databases aren't sophisticated enough to answer that query. And we end up doing a lot of work at the application level. Typically, we extract data from the database, we put it into our processing infrastructure, and then turn that hand like a big pasta maker. This is real time, by the way. And then out comes the answer. And if we're sensible, we will take that answer and we'll push it back into the database. This is an okay thing to do. It's not terribly good for online systems. And because effectively what we're doing is we're breaking the data out of jail, out of the database where it wants to be, we're putting it into our machinery and crunching away on it, and then finally we're taking the answer back and putting it in the database. That's quite different as a model from what we're used to even in the relational world, where of course in the relational world we build a high fidelity model and then we ask questions of that model in order to gain insight. Now, my colleague Alistair Jones suggests that we are at a crossroads which is bifurcated by relational. And on the left-hand side of the crossroads, we have most of the NoSQL databases, where our model is that we denormalize data into keys and values or columns or documents or whatever. And then in order to make sense of that data, we compute an answer over some set or subset of that data. On the right-hand fork in the road, we have the graph databases, Neo4j being one of several graph databases. And in that world, we have a much richer, semantically richer data model, and we query for an answer by traversing across the graph in order to find information goals. And we think that this provides far more expressive power than either the relational databases or the other NoSQL stores. Now you guys, and I'm sorry to the professors in the room, but I will pick on you now. You guys are horrified by this, because the last time you did graphs, there was some professor with arm patches, probably arm patches, and chalk, because professors haven't discovered whiteboards yet. And he's writing blah, 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 big O notation, blah, blah, blah. You're all sleeping behind me, I know how it works, blah, blah. And graphs give people the fear. But you shouldn't fear the graphs. Graphs are lovely. They initially seem difficult because we're so good at relational databases And in fact, I found this myself when I learned or relearned graphs, that the first time I built a system with a graph database, I was desperately nervous because I hadn't done my 3 or 4 or 27 levels of normalization. How many levels are there nowadays in RDBMS? 4? 5? And then of course you get someone who really knows what they're doing and they will denormalize that model for performance reasons. When I first did graph stuff, it was for a telecoms company, and I took a problem that should have taken us 3 years, and I finished it in an afternoon. And that was not a good outcome, because it made me nervous and worried that I had got the answer wrong. Actually, I hadn't. What I discovered was, years later, that problem was very, very amenable to being represented as a graph, which is why it took no effort to solve, virtually no effort to solve. But I felt nervous because I didn't have my rails, my safety rails anymore. I didn't have first, second, third forms of normalization and so on. But once you get over this, this hump and you're here, you love graphs, and you never, ever, ever want to go back to that nasty place of relational stuff. Of course, we live in a world which is full of graphs. In fact, I live in this city, and actually, you know, I imagine some of you may have visited this city before. This is London, represented as a graph, actually. And if I was to tell you, on Friday, I'm going to land here. This is Heathrow Airport Terminal 5. And the Neo4j office is here. This is, I know, not very readable. This is Southwark Station. If I was to ask you guys, particularly those of you that haven't visited London, how do I get from Heathrow Terminal 5 to Southwark? What would the answer be? Some smarty pants will now yell, get a taxi. Thank you. I'm in a startup, we can't afford that. So assuming we're here, well, you know that the rule of this diagram is you can only visit stations that are connected. So you can't magically teleport from here to here. So okay, so we know, so we can visit these connected stations, and then we get here and we can make a choice. And you might choose to go up here, down here, up here, along here, down here, round here, back here, down here. That's one path. That's perhaps a longer path than would be optimal, but it's a valid legal path in the graph. If you are super sensible, actually you'll zoom up this purple line, change a green path. This is where the Queen lives, by the way. You can wave at her as you go past. And then zoom down this silver line to Southwark. And that's actually the shortest path through this graph. So it turns out, shortest path, does that ring any bells? Dijkstra's algorithm, A-star, and so on? Yeah, absolutely. It turns out in our everyday lives, we process graph data without even thinking about it. And now I've just made you think about it, and that's a terrible thing to do. I'm going to make you think about it more. So all this stuff started in the old days. This stuff started 276 years ago with a Swiss mathematician by the name of Leonhard Euler. Notice, as someone who works in IT as a software engineer on the good days, I think this guy represents a certain level of professionalism that we in IT, particularly the men, should aspire to. I particularly like this wig. As someone who is tortured by scratching his head too often at crazy software problems, I do think this is a good look for us. Makes us look a bit more dignified, don't you think? So Euler is an amazing guy. So there's a problem that the Emperor of Prussia wants to visit the town of Königsberg, Kaliningrad nowadays, Königsberg at this point. And although he wants to visit the town, he doesn't want to spend much energy. So he says to the people of the town, I want to visit your town, but I want to cross each of the 7 bridges of Königsberg once and only once, and therefore minimize the amount of walking I have to do. And you can imagine, as the Emperor of Prussia, he has a lot of people at his disposal, and he can send them out and say, go walk. Oh no, I've been on this bridge before. Okay, start again. This is rather a labour-intensive way of, I've been on this one twice. This is a very labour-intensive way of trying to solve a problem. Euler is smarter than that. I imagine Euler is like the first Lisp programmer. So you know what Lisp programmers do? They spend all of their time building the tool, and then a fraction of their time solving the problem. And this is, so this is what Euler does. Euler decides that it would be very inefficient to go walking around Königsberg, mapping out the bridges and so on. So he decides to invent an entirely new branch of mathematics to solve this problem. That's the lazy way of doing it, right? And Euler's critical observation is that the problem has nothing to do with bridges or water or even emperors, although the emperor would be displeased to hear that. The problem is simply about stuff being connected to other stuff. And Euler's observation around this particular graph problem is that in order to meet the emperor's expectations, each blob, let's call them nodes, must have an even number of entry and exit points. Otherwise, you must, by definition, fail the emperor's criteria, which is each bridge once and only once. In fact, in Euler's, in the strictest definition of this, it would be 2. One way in, one way out for every bridge. Clearly, this graph fails that test, which means that Euler was able to demonstrate, although the emperor is super powerful, he can't beat mathematics. And in fact, he would have to cross some of the bridges in Königsberg more than once. Now, if we fast forward 275 years, this graph theory has become an integral part of our everyday lives. We have things like the interest graph, we have things like the social graph, and the graph of internet or telephone system connectivity. We have graphs of something to do with science that I don't understand. But graphs are used everywhere to describe a whole range of problems. This, by the way, not a graph. Not a graph. This is a chart. And as someone who works in graphs every day, I really, really get upset when people use loose English and call this a graph. This is a histogram, or a chart. So great, so we've got graphs, but of course, you guys are super, super skillful at existing data technology. Can't my relational database already do graphs? There's already a book about it, right? Joe Selko's Trees and Hierarchies in SQL for Smarties. So I can read that book, and then I should be able to do some kinds of graph in my SQL database. Well, okay, maybe. There are a few problems with this approach. SQL databases, or the manifestation of the relational calculus on SQL databases is that you have a big set-based platform. And ultimately, when you are joining, particularly doing recursive joins to try to emulate path finding in a graph, you're simply building up massive internal sets of data, the intermediate set problem or the join bond problem as we know. So there is a practical limitation to what you can do in a set-based database when you're emulating paths. The other thing that kind of makes this difficult is I read this book, I got this book, and I thought, wow, that's the most arrogantly titled book I've ever seen. Because you must be a smarty to read it. Now, I'm no university professor, but I do have a PhD that I bought off the internet. And I thought, wow, that makes me a smarty. I can read this. And I got a few chapters in, and he defeated me. So I hate that book. So no, your relational database can't do that, because there's an awful lot of complexity inherent in that model. Oops, back a bit. Come on, there we go. They're going to retract my internet PhD at this point. So even for simple cases in the relational world, we end up introducing complexity. Now you guys don't even see this as complexity anymore, do you? The join table. Well, but that is a natural manifestation of the use of a relational database, Jim. Are you stupid? Oh yes, I must be stupid. Because when I first learned, so coming from a background, as I did, and we've done our relational calculus, and we've done some relational algebra, and we're quite comfortable with that, and then they let us loose on a database, a real database on a Unix time-sharing system. I am that old. Youngster, I am that old. Yeah, you can't believe the stuff I'm saying. I'm like an old version of Harry Potter to you. When I discovered these things, why am I telling the database how to do its job? And worse, just all this describes is that many customers can have many accounts. You can imagine that these things, that's a very common idiom, many to many. These things crop up everywhere. And so all I want to describe really is this, that Alice owns this account and she also owns this account. Bob owns this account, and he owns this account. Now if I want to ask questions like, which accounts does Alice own? I find Alice and simply find the account she owns. If I want to find out who is the owner of this account, I simply follow the owns arrows the other way. That's the model I want. That's the domain. This isn't domain. Ah! See? SQL databases destroying my presentation. This isn't the domain. This is accidental complexity. And we also know about the other characteristics like join models and so on, which make this stuff really, really difficult. Actually, if you were to decide to model this domain in a graph database, it would look like this. Oh, exactly the same. In fact, in a graph database, we call these things relationships. We call these things nodes. And in fact, the entirety of the Neo4j model can be summed up on one slide. When you learn the SQL stuff, you had to read the book that was this thick. To learn about graphs, you need one slide. Although I am cheating because it's a widescreen slide, so I get a few more characters. But really, this is it. We have nodes, and the nodes can be labeled. And the label gives you the semantic context of the node in the network. Nodes represent entities. And in those nodes, we can have properties, the user data that we want to store, username, account balance, and so on. Connecting those nodes, we have relationships. And relationships are directed. They are named, so you know what the relationship means, and they can also have properties on them for things like weighted graph walks and so on. So you can start to express things like Alice loves Bob. Of course, that doesn't imply Bob loves Alice because the relationships are directed. In fact, we're in IT, so we know that only too well. We've all been there, particularly the gentleman in the room, where gentleman loves lady in a different department. Lady in different department does not know that geek exists. Sometimes there is an asymmetry in graph modeling, which is important. So that's it. So how would we apply this stuff? So the second thing I ever did with a graph, and I feel treacherous towards Marco now because it wasn't with him. I was working with another retailer. I'm sorry. It's like having an affair, isn't it? I was working with some inferior retailer. Is that better? Okay. I was working with some inferior retailer, and back in the day, it turns out that loyalty cards had been invented, but most of this stuff wasn't really science. And what would happen is, in the UK, you would go to the supermarket, you buy your groceries, and then you swipe your loyalty card. And then a week or two later, you'd get a letter at home from the supermarket, which you'd pick up and say, oh, that's spam from the supermarket. And you'd immediately put it into the rubbish. From the supermarket's point of view, that's not a very, very useful way of communicating with you, and it's not a good way of changing your buying behavior. Now, it turns out the psychologists that the supermarkets employ, and you must have these people, right? I thought the psychologists that I went to university with were all serving fries in McDonald's. No, 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 no. They are clever, clever people, and they are inside our heads. And what they know is that humans mostly are not psychopaths. Mostly. And this often works for me. Thank you for not being a psychopath. That's not my card, by the way. It's a wonderful thing about humans that when we engage with one another, it's a really difficult thing. If I put something in your hand, it's really difficult for you not to look at it. Now, if that thing wasn't Lorenzo's business card, if that thing was a voucher offering you money off some groceries or some high-value item that you want, the act of giving it to you and then you looking at it makes you so much more likely to act on that voucher. If I put the voucher in the mail to you, very unlikely that you'll act on that voucher. So what do we need to do then? What we need to do is be able to provide recommendations in real time. Now, when we did this proof of concept, in real time meant while the customer is at the checkout. Now, of course, that also could mean while the customer is on your website in the clickstream nowadays. And so we wanted to build a system that would make great recommendations right up to the last millisecond. And so we thought about this, and we thought there are at least two interesting graphs here. And our design was influenced by a story we heard. And we heard that in the United States, Walmart, the big supermarket, hypermarket chain, has this thing where on Friday nights, they put beer on the end of the aisle selling nappies. And on Friday nights when they do that, they sell more beer and more nappies. And we thought that was really interesting. We don't know if it's true, it's like an urban legend, but we liked it. So we thought we would look at beer and nappies, right? So, two fundamental needs of mankind right there. So what did we do? Well, we built out a hierarchy of products. This is one graph, actually. And you can see here that I have things that are more general towards the top of the hierarchy, and things that are more specific towards the bottom. So here I'm saying that Stella Artois is a kind of beer, which is a kind of alcohol. And dry nights are a type of nappies, sorry, American English. I'm afflicted by Americans in my company, which are something to do with baby. And then down here we've got Xbox, which is a kind of game console, which is a kind of electronics. So there's a kind of hierarchy at work here, a taxonomy actually. And the other interesting graph we had was customer history. And it turns out that these two graphs intersect. So for example, Mike has bought some Stella, he's bought some Dry Nights, and he's bought an Xbox. And we like this pattern, because this pattern we can name. And we said, actually, this is the young father pattern, because we think the semantics are that he buys nappies because he has a baby at home, and because he has a baby at home, he can't go out and party with his friends anymore. His life's a bit crap. So what can he do? Finally, the baby goes to sleep, and all he wants to do is drink a beer. I'm speaking from experience here. Have pity on me. That's all he wants to do. That's all he's good for at this point. Which is interesting, because it means that this guy, Joe, is almost meeting the same pattern. We see that he's bought beer and he's bought nappies, but that he hasn't bought anything in the game consoles. So that's interesting, because that could be an opportunity to sell him a game console, right? So this is a candidate young father. Slight caveat. That was one of the interpretations of this data. The other interpretation of this data was extremely hardcore gamer.
Yeah.
You can't unsee that, I'm afraid. That's now in your heads for always, and you are damaged by it, I think. Anyway, so what can we do with this stuff? Well, actually, one of the lovely things about having your data in a graph format is that querying it becomes a joy. In fact, one of the lovely properties of graphs is the structural quality of a graph lends itself towards the query. So if you have this graph here, you can use this query here to ask about candidate young fathers that should be given vouchers for Xboxes or whatever. Now, this is called Cypher. It's Neo4j's query language. How many of you guys know Cypher? Brilliant, 0%. I say that you might do. By the end of the next 30 seconds, you will all know enough Cypher to be awesome. This stuff is easy. The match keyword says, hey database, find me a pattern. And the pattern I'm interested in is where I have a customer node, so a kind of ASCII art for graphs, which has an outgoing bought relationship to something I don't care about, which itself has an outgoing in relationship at any depth to the category of baby. So that's saying, hey, find me whether I've got a customer that's connected anywhere in the hierarchy of baby stuff. Same again here, find me a customer which has bought something in the category of beer. So find me where a customer has a bought relationship anywhere underneath beer. And then finally, find me that same customer where I have an outgoing bought relationship to the category of console, gated. That is where I do not have any connection underneath game consoles, and tell me that customer. That's an opportunity to give the guy a voucher such that you can now change his buying behavior. In Neo4j, crossing one of these relationships on my laptop, which is lovely and new and shiny, and I love it, costs about, hello baby, 1/13,000,000th of a second in a steady state database. Because under the covers we're just doing pointer chasing. There are no global indexes to look up. This is simply multiplying, and it turns out that CPUs are quite fast at that. Of course, the argument set against us was we can already do this with Oracle, because of course everyone knows you can already do everything on Oracle, especially if one of those main features you're looking for is paying Oracle. If that's one of your primary features, they have got you covered. And so the Oracle guy said, well, this will just, what we'll do is we will pre-compute the recommendations in a batch job overnight, so that each day the customers have a fresh set of recommendations. And that's simply not good enough, it turns out. The psychologists were helpful here. It turns out that if you have a poor shopping experience, you will tell 17 of your friends and family about that experience. What I can surmise from that is you need to have more of an exciting life. But it turns out statistically, something bad happens in a shop, you will tell 17 people. And of course, this is in the old days before Twitter. So now, when you have a bad experience of a shop, you will tell 17 people on Twitter. Because, you know, we don't magically have new friends because of Twitter. You will tell those same 17 people. And what happens if you pre-computed the recommendations is this. Beep, pancetta. Beep, garlic. Beep, orzo. See what I did there? That's dinner for you, you're welcome. Oh, come on, that's a good recipe. Is that not living up to your standards of high quality peasant Italian food? I'll go to Sicily next time. Beep, Xbox. Beep. Now I'm going to ruin it for you. Brussels sprouts, there you go. Finish the transaction, voucher is printed, 20% off, PS4. That's a contraindication, as the psychologist told us. And what it means is, it's not great when you give someone like a boring or unexciting recommendation. €1 off Brussels sprouts does not make anyone happy. But it's really bad when you actively look like you're ridiculing the customer. Yeah, I've just bought an Xbox, you print me a voucher for a PS4. Amazon does this all the time, right? It's like, I bought, like, a couple of years ago, I was buying baby stuff, I bought a pushchair. Ah, you bought a pushchair. You may also like to buy these pushchairs. Gee, thanks, Amazon, you genius. But you see how that's going to make the customer really unhappy, because now they feel that they've gotten a poor deal, and they will go and tell their 17 friends all about it. The problem is that the recommendation did not take into account data right up until the last moment, because of the nature of the data processing infrastructure, big, clunky, set-based databases, they simply couldn't do it in real time. So, I think we can do this not only in real time for runtime, I think we can do this in real time in terms of building the stuff. Does anyone believe me? No. Okay. So I've got a copy of Neo4j installed here, and I'm going to run it. That's it. Fresh copy of Neo4j, nothing in it. Just running it. Thank you. And now I'm going to flip open, there we go, Neo4j browser. Woo! Really? Well, that almost never happens. Uh-oh. That was slightly weird. Oh, no way! Oh. Now I've lost the crowd. You know, I've done this demo about 10 times, and it never goes wrong.
What I do have, though, is a copy of the last time I did it, which is great, because it means I can use that one. No, you think? Oh, okay. So you think I can do... Well, that's a really crap bug anyway, then, right? No. Oops. I really hope that's not so. No. All right. What I'm going to do? Oh, I'm losing the crowd. This is too bad. All right. I'm going to go into. Alrighty. That's what you get when you get the bleeding edge software. Let's see what happens this time. I am perplexed. Oh, I know why. There we go. It was the hotel Wi-Fi into trying to get off. Anyway, as I was saying, that took longer than the actual demo is going to take. This is the Neo4j REPL, and I've got some data in this database, which you can see is it's a bunch of shopping data. And what I've got in here is customers, and I've got baskets that they have bought or that they're currently working on, and I've got a bunch of, not too many of them, you can see products. So the data model is customers buy baskets, and baskets have links to the products that are in them. There's also, as you can see here, some social data. This is cheating, by the way. Supermarkets really don't have social data in them. They actually have some very sophisticated ways of understanding demographics, but that would be too hard to show you tonight. So I've just cheated and said we have some social data between them. So what can we do then? Given this, realistic supermarket data, what might we do? Well, we can do a bunch of things. So firstly, we might just ask the supermarket what its top selling products are. And that's what this query does. It says, hey, database, find me a pattern where some customer has bought something, has bought a basket which had some product in it. Return the product, return the count of the product, order by the count of the product, descending, and limit to 5. Tell me the top 5 most popular bought items. If we run that, we get this kind of answer back, which is not so helpful when it's pictorially represented that way. But you can see that we have things like butter, unsliced bread, tagliatelle, tea bags, whole milk. It's a very strange supermarket because I made it up on an aeroplane. So that's fine. That's actually some insight. It will allow the supermarket to arrange its supply chain so that it can guarantee all of these things are always in stock. Now, for you and I, that's not very compelling. For my mum, super compelling. She loves to buy top-selling items. I have no idea why. She buys the randomest stuff because of it, but #1 brand, she will buy it. So this is kind of helpful for people who don't know better. This is one recommendation we can make. But perhaps a better recommendation is to tell me about the stuff that I like. So the supermarket, the online supermarket I use, always gets me. I buy my stuff and it's like, salad and fruit, organic this and blah, 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 blah. And then at checkout it says, but you really like this particular chocolate. And I'm like, yes I do, give me. So that's a better recommendation because that always forces me to act. So how does that recommendation look? Well, actually, it's pretty similar. So let's whack that in. Oops. So here, a similar recommendation, except, so it's again, find me, hey, database, find me the pattern where I've got some customer that bought some basket, where I had some products in that basket. That's the ASCII art pattern I'm looking for. Now I'm saying, actually, I'm looking for a specific customer. This is the currently logged in customer, or the customer at the checkout right now, Alice. And then tell me about Alice's products. Count the products, ordered by the count of the products in ascending fashion, limit 5. Effectively, tell me Alice's top 5 products. Alice has only ever bought 3 products, so we get these ones. So now this is telling Alice about her purchasing history. This is a great reminder query. Hey Alice, you haven't bought that chocolate you really like. You should definitely buy that. That's another recommendation that the supermarkets could implement on Neo4j if they would talk to me after this event, and I'll give them very favourable licensing deals. So, that's all good. What else might we do though? It turns out that humans, well, we're a bit tribal. And although it's nice, one reasonable recommendation is popular things. Another good recommendation is things that I find popular. But a really strong recommendation is stuff that my friends and friends of friends are buying. Because none of you needed an iPhone 6. None of you. You all have that iPhone 5S. It's only like 6 months old. For the first time someone bought an iPhone 6 into your office, oh, you must get an iPhone. Oops, mine's broken. Peer pressure is a stupendous way of forcing people to buy things, right, Marco? He knows this. So why don't we do that then? So I said that we have some social information in this. Really, in a real production environment, this would be sophisticated demographic information. But this query is in 2 halves. It says, hey, database, find me a pattern where I've got a customer that has an outgoing friend relationship at depth 1 or depth 2, friend or friend of friend, to another customer. Make that customer Alice, because she's the currently logged in user, and make sure that the customer and their friend are the same. What? Oh, because friend of friend could be me. So we want a donut shape around me, but we don't want to include me in this. And then we're going to take all of those friends, and then we're going to pipe that into the second part of the query, which now looks very familiar. Hey, database, based on those friends, tell me about those friends which bought some basket, which had some products in, return the products, return the count of the products, ordered by the count of the products in a descending fashion, limit 5. This is tell me the top 5 things bought by my friends or friends of friends. Because it turns out you need to buy those, or you're not cool, right? If your friends come round and you haven't bought the same stuff that they have, you're weird and strange. You are an outcast. So when we run that, we see that Alice should be buying tagliatelle, unsliced bread, cereals, whole milk, and tea bags. This is a weird set of friends that she has. It's like she has like one, Italian friend, and then this is very English here. I don't know, she's quite multicultural, is Alice. And she just likes awful bread. Where we go? So then the final thing that we might do in 5 minutes is upsell. So in our data set, we have a misspelling. I'm sorry about that. We have some links in our data that tells that describes products that go well with other products. Bread goes well with olive oil. Milk goes well with tea. That's what we do in the island. We do weird things, and so on. And this can either be, this knowledge can be injected by a human user, or more likely, this knowledge can be injected by a machine learning algorithm, which spots useful pairs of products. And then we can act on this information such that if I have tea in my basket, I should be also recommended milk to go with that tea. And that's what this does. It says, hey, database, find me any customer which is currently working on a basket, so this is the current shopping basket, and where in that basket I have a product. This is the anonymous node, so I don't really care what this is, but where it has, current basket, which has a product in it which is complementary to some other product. where that customer is Alice, tell me about the complementary product. So if Alice has a toothbrush in her basket, we should recommend toothpaste. If she has bread in the basket, we recommend butter, because we don't have olive trees in Northern Europe. And if we ran that, we find that Alice should be recommended these things based on what's currently in her basket. So you've got that machine learning angle to it as well. See, 5 minutes, sort of. So, given that, pretty convincing, you know. Oh, I don't know, Marco. Walmart is doing this kind of stuff on Neo4j because it's just very easy to work with. You know, describing a graph of dependencies, describing a graph of purchases, that recommendation as a graph is a natural fit. I did zoom that especially for you, by the way. It was absolutely fixed deck. Let's see that again. Oh, what a surprise, Walmart. The point being, so although we have talked about graphs, particularly in a retail and recommendations scenario this evening, graphs are very, very, very applicable to a wide range of scenarios. About a year ago, I met with the guys at NASA. They use graphs to do mission planning. And they found a lovely problem with one of their satellites, which had a zinc and nickel electrical connector, which would have caused a short circuit in orbit. And of course, when they traverse the graph and they find these incompatible connectors, they're able to make a change and make the mission safer. Blew me away. You've got telecoms that do, obviously, networks are a graph. You've got financial services people looking for patterns which are fraudulent in laundering money through the system. You've got these guys, eBay. Ever heard of them? Doing deliveries, real-time deliveries of your old laptop to my house within an hour, based on some graph theoretical stuff. So the graph isn't just a niche thing. It isn't a thing that we learned at university and hated. It isn't just that thing for social. It turns out that graphs are very applicable. And I think if I look back on my career in IT, 90% of the things that I shoehorned into a relational database, sometimes with actual physical violence, would have been far better represented as a graph, and it would have left me with far more hair. So, if you're interested in graph stuff, there's a bunch of resources out there that you can now grab. This book and this book are available for free. If you go to your eyes, graphdatabases.com or neo4j.com, you can get full ebook versions of those. And if you want to do some interactive graphing, also at neo4j.com, you will find an interactive course where you can learn the graph and type stuff in and get feedback and so on. It's really lovely. And that's all I have. Thank you so much for listening this evening.